Welcome to this comprehensive tutorial on C# code optimization, designed for beginners looking to enhance application performance and efficiency. This guide will cover essential techniques to build responsive and efficient applications, setting the stage for a deeper understanding of C# development best practices. Optimizing your C# code is crucial for creating responsive and resource-efficient applications, ultimately leading to a significantly better user experience. Unoptimized code can result in slow loading times, high CPU usage, and increased memory consumption, all of which negatively impact user satisfaction and overall application stability. Our journey begins with profiling tools, which are essential instruments for identifying performance bottlenecks within your code. These tools provide data-driven insights into where an application spends its time and resources, making the optimization process systematic, effective, and targeted. Visual Studio offers a powerful suite of profiling and diagnostics tools, easily accessible through Debug Performance Profiler by pressing Alt plus F2, or directly via the Diagnostic Tools window that appears during debugging sessions. These integrated tools provide comprehensive analysis capabilities right within your development environment. For detailed post-mortem analysis on release builds, the Performance Profiler is the ideal choice, offering in-depth insights into your application's behavior. Conversely, the Diagnostic Tools window provides real-time insights during active debugging sessions, allowing you to monitor performance and catch issues as they occur. JetBrains.Trace is another prominent .NET profiling tool, offering detailed performance analysis for various application types, including desktop, web, and mobile. It provides deep insights into CPU usage, memory allocation, and I/O operations, making it a powerful alternative or complementary tool for developers. The CPU usage tool is a primary resource for analyzing CPU resource consumption, specifically pinpointing top functions and hot paths that consume the most CPU processing power. This allows developers to focus their optimization efforts precisely on the code sections that will yield the greatest performance improvements. It provides a detailed call tree view, which is crucial for understanding execution flow, distinguishing between total CPU time, which includes the execution time of all called functions, and self-CPU time, which measures only the time spent within the function's own code, excluding its children. This distinction is vital for accurate bottleneck identification. The Memory Usage tool helps evaluate an application's memory consumption and identify potential memory leaks, though these are less common in .NET applications due to automatic garbage collection. Nevertheless, this tool is vital for detecting inefficient memory patterns or subtle leaks that can impact long-term performance and stability. You can take memory snapshots before and after a suspected issue to compare changes in object counts or heap sizes, revealing precisely where memory might not be released correctly. For example, an increase of 3,492 bytes for class handler store objects between snapshots would indicate a potential leak. The .NET Object Allocation tool specifically identifies allocation patterns, anomalies, and common garbage collection issues, typically running as a post-mortem analysis. It helps pinpoint excessive object creation, which can trigger frequent and costly garbage collection cycles, even if memory isn't technically leaking. Instrumentation, similar to the CPU usage tool, offers more precision with exact call counts and wall clock time for each function, though it comes with a higher overhead during profiling. This tool is used when extreme accuracy in execution timing and call frequency is required, despite its slight impact on runtime. File I/O tools are essential for optimizing file operations and diagnosing slow loading times by showing detailed read and write activities. These tools allow developers to identify bottlenecks in file system interactions, optimize data access patterns, and significantly improve application responsiveness, especially during data-intensive operations. For asynchronous code, the .NET Async tool analyzes performance in .NET Core and .NET 5+ applications, showing the start, end, and total times for async operations. This provides crucial insights into the behavior of concurrent tasks, helping developers understand potential delays, identify deadlocks, and ensure efficient execution without blocking the main thread. The database tool records and analyzes database queries for .NET Core and .NET 5 Plus applications using ADO.NET or Entity Framework Core, showing query start times and durations. This tool is invaluable for optimizing data-driven applications, as it allows developers to pinpoint slow or inefficient database queries and improve data access layer performance. .NET Counters, available from Visual Studio 2019 version 16.7, visualize live performance counters such as CPU usage, garbage collector heap size, and other critical metrics. These provide a real-time dashboard into an application's health, offering immediate feedback for observing the impact of code changes or identifying transient performance spikes. Perf tips provide quick performance information directly in the code editor during debugging, showing event durations for specific code blocks or functions. These small, in-editor pop-ups offer immediate feedback on execution time, allowing developers to quickly spot performance hotspots without needing to switch to a separate profiling window. For XAML applications, the application timeline analyzes resource consumption related to UI frames, network/disk requests, startup, and page loads. It helps diagnose UI responsiveness issues by visualizing events like layout passes and rendering, allowing developers to identify causes of low frame rates or high UI thread utilization, such as a layout event for a grid control taking 57.53 milliseconds. The GPU usage tool examines GPU activity in direct 3D applications, helping determine if performance bottlenecks are CPU or GPU bound, and accurately assessing frame rates. For graphics-intensive applications, this tool is essential for ensuring smooth visuals, for example, by aiming for one present call between every two vsyncs to achieve a consistent 60 frames per second. Visual Studio Copilot can recommend appropriate profiling tools, analyze identified performance issues, and provide targeted assistance based on your specific code context. It acts as an intelligent assistant, leveraging AI to suggest solutions and streamline the entire optimization process, making it more accessible for beginners. These powerful profiling tools also support cross-platform scenarios, extending their capabilities to applications running in Windows Subsystem for Linux, Docker containers, and native Linux environments. This ensures comprehensive performance analysis across diverse deployment targets, providing flexibility for modern development workflows. Next, we delve into memory optimization, focusing on how your application uses memory and preventing common issues that can lead to performance degradation. This section will explore strategies to efficiently manage an application's memory footprint, ensuring stable and long-running performance. While .NET's garbage collection automatically manages memory, understanding its behavior, including its generational approach and collection triggers, is key to efficient memory usage. A deep understanding allows developers to write code that cooperates with the GC rather than fighting against it, leading to more optimal memory management. The .NET Object Allocation tool helps identify patterns that might lead to inefficient garbage collection cycles or excessive allocations, even with automatic memory management. It specifically highlights scenarios where frequent object allocations, even if short-lived, can put undue pressure on the garbage collector, leading to performance degradation due to increased GC pauses. Identifying and avoiding memory leaks is crucial, even if they are less common in .NET applications compared to unmanaged languages like C++. Despite automatic memory management, leaks can still occur due to specific coding patterns, leading to gradual memory consumption and eventual application instability or crashes. The memory usage tool is vital for detecting these subtle leaks, and the recommended approach involves taking 2 memory snapshots at strategic points. This functionality allows you to capture detailed snapshots of the application's memory heap at different times, forming the foundation for effective leak detection. To effectively pinpoint memory issues, take one snapshot before a sequence of operations suspected of causing a leak, and then take another snapshot immediately after those operations are completed. This methodical approach ensures that any changes in memory usage directly correlate with the specific actions being tested. Comparing these 2 snapshots reveals objects that have increased in count or total size, precisely pinpointing areas where memory might not be released correctly. For instance, The heap diff view can show significant increases in count difference and size difference for specific object types, such as class handler store, indicating a memory leak. Common causes of memory leaks in .NET include unreleased event handlers, where an object remains referenced by an event source, static references that prevent objects from being garbage collected, or improper disposal of idisposable objects, leading to unmanaged resources not being released. To prevent memory accumulation, always ensure you properly unsubscribe from events when they are no longer needed, and consistently dispose of idisposable objects by using statements or explicit dispose calls. These practices are fundamental for timely resource cleanup and preventing leaks. Finally, we briefly touch upon plugins and interoperability, specifically focusing on C# interop with C++ and DLL imports. Understanding how C# applications can interact with external, unmanaged code is crucial for extending functionality and leveraging existing native components. While a detailed demonstration of C# interoperability is beyond the scope of this tutorial due to source material limitations, understanding the underlying concept is incredibly important for advanced development. Grasping these fundamental principles will enable developers to explore and implement these techniques when specific project requirements demand it. C# can interact with unmanaged code, such as C++ DLLs, using a mechanism called platform invoke, or p/invoke, to call functions directly. P/invoke is the primary method for C# applications to seamlessly integrate with and execute code from unmanaged dynamic link libraries. This powerful capability allows C# applications to leverage existing native libraries, significantly extending their capabilities and performance in specific scenarios. By using p/invoke, C# developers can tap into a vast ecosystem of high-performance native components that might be difficult or inefficient to implement purely in managed code. In summary, mastering profiling tools and memory optimization techniques is absolutely fundamental for any C# developer aiming to build high-quality applications. These skills are not just for advanced developers, but are essential for creating robust, high-performance software. By effectively using powerful tools like the Visual Studio Profiler and developing a deep understanding of garbage collection principles, you can significantly improve your application's performance and responsiveness. Proficiency in these areas empowers developers to diagnose and resolve complex performance bottlenecks efficiently. To truly excel, continue exploring and practicing these techniques diligently to write more efficient, robust, and high-performing C# applications. Continuous learning and hands-on application of these optimization strategies are key to becoming a proficient and effective C# developer.